It is section 5.3.5, Nonlinear Support Vector Machine and Kernel Trick. A reason why the SVM is popular is that it can be easily kernelized. That means it can be easily non-linearized to handle inseparable data. The basic idea behind kernel method is to transform the data to a higher dimensional space where the data becomes linearly separable. Look at this example. This data has two classes, and there is no line which can separate the data. So the data is inseparable. However, if we transform it to the three-dimensional space by adding one more component, the square of distance, the distance is measured from the origin to the point. Then the data becomes linearly separable, and outer points will be on the upper portion and inner point will be on the lower portion, so that we can find a plane to separate them. So it becomes separable in the three-dimensional space. Once we transform back to two-dimensional space, then the hyperplane is corresponding to this circle. So the method will work very well. This is the basic idea of kernel method. In the higher dimensional space, and the data becomes separable. To solve a nonlinear problem using an SVM, we should transform the training data to a higher dimensional space using a mapping phi and train a linear SVM model. The hyperplane is the result of a linear SVM. And at the test stage for new unseen data, we can classify using the same mapping phi and the same linear SVM model. And now here we'll see the dual problem. Recall the dual problem to the soft margin SVM. Here we have observation. The objective is a linear combination of dot products xi and xj. So if the kernel SVM transforms the data samples through the expansion function phi, then the dot product xi xj must be replaced by phi xi dot phi xj. Now the dot product is performed in a higher dimension so that this dot product can be expansive, and expansion is also expansive. So to avoid the expansive state of explicit computation of the dot product, we may define a so-called kernel function k xi xj, which is used for replacing this explicit dot product. It can be an approximation. It can be a function related with xi and xj. One of the most widely used kernel is the radial basis function RBF, or simply called the Gaussian kernel, which is defined in this way. Once xi, xj are near each other, then this value will be small, so that the exponent of negative gamma and this norm squared will be around 1. If they are far away, xi, xj are far away, then this norm squared will be large, and then along with the negation, the value will be around 0. So we may consider the kernel as a similarity function. And here the idea is just simply we try to change the phi xi dot phi xj with a kernel function, so we don't have to worry about the explicit expansion of the data points and dot product in a higher dimensional space. That is the big picture behind the kernel tree. That is introduced to save complications and expensive computation. And in implementation level, it can be easily changed. Only the difference is that the dot products are replaced by kernel functions. Let's go back to page 115. Here we have a summary of the support vector machine. For this dot product, xi, xj, and we replaced it with k, xi, xj, a number. And in the test stage also, x dot xi must be replaced with k x xi. Okay, so by replacing these dot products with kernel value, we can solve the problem then so that it can be easily kernelized. Just a simple change. Okay. Now there are common kernels, polynomial of degree exactly k. Here xi, xj, dot product with k power, and polynomial of degree up to k by adding a constant. Now this will be a polynomial of degree k. Now we can use also sigmoid kernel function such as hyperbolic tangent, and this is a Gaussian RBF we already considered. There are many other kernels, for example, Fisher kernel, graph kernel, string kernel, and so on. And you need to choose appropriate kernel for new data set. So it is a very active area of research. Let's look at this example. Here, kxj, kxz is defined in this way. So it is a quadratic kernel. And if we use sum algebra, then for this term, we can reach at that. Now, in order to express kxg as a dot product, we try to define future expansion. Now, from x1 to xm, we expand the vector into this way, and that is in R m squared plus m plus 1, much higher dimension. Then you can check that phi x and phi z is the same as the kernel function of xc. It is simple. However, if you try to do explicit expansion, then it can be very complicated. For kernel functions, the kernels may not be expressed as phi like this dot product. For example, the Gaussian kernel cannot be expressed as this dot product. And many of them, many of kernel functions are not expressible as dot product. The mapping phi may transform x to infinite dimensions. For some kernels, if you try to find the explicit expansion, then sometimes you can see that the mapping is now the transform the given point to infinite dimensions. Okay, here we have a summary for linear classifiers they are a simple and popular way to learn a classifier. They suffer from inefficient use of data, overfitting, or lack of expressiveness. For SVM, it can fix these problems using maximum margins and feature expansion. So it is a non-linearization, and mapping is to a higher dimension. In order to make a feature expansion computationally feasible, to save the complication and expensive the steps, and we need to use the kernel trick. So by using these three things, SVM becomes so popular. Here we have a final remark, and the kernel trick. In kernel trick, there is no explicit feature expansion. However, the kernel must be formulated meaningfully. That means that the kernel function must be considered as a nonlinear measure for the data to become separable. If you consider the kernel function as some algebraic addition and through trial and error manner try to find a kernel, then it may not be meaningful. So you have to be a bit careful in the choice of kernel function, so that it must be really a nonlinear measure for the data to become separable. Okay? Thank you.